Given the root of a binary search tree, and two distinct nodes P and Q that both appear in the tree. Return their lowest common ancestor, the deepest node that has both P and Q in its subtree, where a node counts as a descendant of itself. Constraints: between 2 and 10 to the 5th nodes, all values are unique, P is not Q, and both nodes exist in the BST. Example 1, P is the node with value 2 and Q is the node with value 8. Every ancestor of both includes the root 6, 2, and 8, the deepest such node is 6, so the lowest common ancestor has value 6. Start your pointer at the root, 6. Both targets live in the tree, P is 2 and Q is 8. In a BST, smaller keys are in the left subtree and larger keys in the right, so from 6, 2 is to the left and 8 is to the right. The general rule: while both P and Q lie strictly on the same side of your current value, you descend into that subtree and you have not yet passed the fork that separates them. Because the tree is a BST, you never scan the whole tree. At the current node, compare both P and Q. If both values are smaller than the current node, both targets lie in the left subtree, so move left. If both are larger, move right. If neither of those holds, the current node lies between them, or equals one of them, stop, that node is the lowest common ancestor. For P equals 2 and Q equals 8, at the root 6 we are not in the both smaller or both larger case. 2 is on the left and 8 on the right, so the paths to P and to Q diverge at 6. That makes 6 the lowest common ancestor. Any step deeper into only one subtree would leave the other key behind. We start at the root. Fix the interval from min of P and Q to max of P and Q, here 3 to 5. At each step ask, is the whole interval strictly to the left of the current value, strictly to the right, or does the current value sit inside? If both targets lie entirely on one side, the lowest common ancestor must live in that subtree, so we step there. Because the keys are in sorted order in the tree, when we commit to the left or right child we never need the opposite branch for this pair. That branch cannot contain both P and Q, so we treat it as gone. Each move cuts away an entire subtree, that is the filtering descent, and it is why the walk is only O of height. Finally, the current value lies inside the closed interval from min to max, or equals one endpoint. There is no single child that still contains both targets, the paths to P and to Q fork here, or one target is the node itself. Stop, this node is the lowest common ancestor. Same tree, new pair, P is 2 and Q is 4. The interval from min to max is 2 through 4. At the root 6, the whole interval lies to the left, so we discard the right subtree and move to 2. Now the current value 2 lies inside that closed range, it is even the left endpoint. We stop, 2 is the lowest common ancestor. When one of the two nodes is an ancestor of the other, that ancestor is always the answer, there is no fork step. Let n be the number of nodes and h the height of the binary search tree. Time is O of h in the worst case, we walk down at most one edge per level until the current value lies between P and Q. If the tree is skewed, h can be about n, so worst case time is O of n, space is O of 1 for the iterative version, only a few pointers and scalars. A recursive solution would use O of h stack space. Iterative version, set A to the smaller key and B to the larger, then walk a single pointer from the root. If the current value is below both targets, go right, if above both, go left, otherwise you are at the lowest common ancestor, so return that node. Constant extra space. Recursive version, compare both P and Q to the current root. If both keys are smaller, the answer is in the left subtree, so recurse left. If both are larger, recurse right. Otherwise the root lies between the two keys or equals one of them, so the root is the lowest common ancestor. Each call uses stack space proportional to tree height.